Okay, welcome to the 8th class meeting. Last time, we studied the harmonic series representation of a Y-sense cyclostationary random process. And simply put, this is the harmonic series representation. So you have the Y-sense cyclostationary random process with cycle period capital T. And it is now written as a summation of band-limited random processes limited to the Nyquist zone plus minus 1 over 2t, where capital T is the cycle period. And here you have harmonically related complex sinusoidal signals. And its fundamental frequency is nothing but the 1 over capital T. Again, capital T is the cycle period. Got it? So whenever you have a sum of functions, sum of terms, we call it a series, right? You have a sequence. If you add them up, partial sum sequence is called the series. So this is a series. That's why this representation, which means that rewriting, right, is equivalent or identical in this case. Copy of it is a series. Got it? It's similar to Fourier series, right? In Fourier series, what do you have? You have complex sinusoidal signals with frequency 1 over period apart. And you had here what? Constant coefficients. Now, what's the difference? This is a random process. And here, not only this harmonic series representation claims that a Y-sense cyclostationary random process can be written in this way. Here, what is the most important property of these random processes? So in Fourier series, you didn't have a random processes, right? Now you have strictly band-limited random processes. What is the most important property of these random processes? They are jointly Y-sense stationary. Got it? So this equation or this representation claims that a Y-sense cyclostationary random process is equivalent to what? A vector Y-sense stationary random process. Got it? Another thing is this. So let's see the property of a vector Y-sense stationary random process and see its frequency domain property. Last time I little bit mentioned what was going on. Anyway, consider a vector valued Y-sense stationary random process x of t. Here, this, you may say, lemma is very general. The component random processes needs not to be strictly band limited, needs not to be not only strictly banded, but also band limited to the Nyquist zone. Okay, so this is a very general property. A vector valued Y-sense stationary random process x of t has its matrix valued power spectral density in the form of where f is the element-wise continuous parameter Fourier transform. So in this case, parameter means delay, tau. And we may say and find that the ij's element of this matrix is nothing but the cross PSD. It's not just invented notation by myself. People really use this lowercase x PSD to mean cross PSD. And whenever I confront this x, I still remember the strange sign I've seen when I went to the US. There was a traffic sign saying pad sing or sing. Pad sing, I didn't know. And this is read what? Pedestrian crossing. So X means cross. Got it? Which means in Korean, 횡단보도. Got it? And actually, that mark was put just next to the railway, not just ordinary pedestrian crossing, 횡단보도, especially for the train system. Got it? Anyway, so X is read cross, means this is cross PSD. Got it? Anyway, so this is simply an amazing thing because in the first class meeting, I talked about the spectral correlation of a random process. And you may remember something interesting. For example, I said, suppose you have a linear filter with impulse response, linear time invariant filter with impulse response h1 of t and another one with h2 of t. We call the output of the first LTI filter as y1 and the next as y2. Then what was the most important result? They are jointly y-sense stationary, right? Actually, you learned about this result, or possibly learned, in your undergraduate and graduate probability in random processes course. And also, at that time, I talked about the cross power spectral density, right? And it was defined as the limit of the time limited, sorry, y1 and y2. Limit of the cross correlation of the time limited or time truncated random processes properly scaled by window length 2 delta. And if this limit exists, it is called the cross power spectral density. And let's see the definition of cross power spectral density. What does this mean? Even though it's a truncated version's Fourier transform, anyway, it contains the information about the frequency component of y1 around a specific frequency f, right? And what is this one? This is the same. This is the frequency component of in y2. Now you compute the correlation. right? So what does this mean verbally? This is nothing but the cross correlation between the frequency components of the same frequency, but in two different random processes, right? And here, especially in this setting, so this is general definition. Capital G means something general. And this is somewhat special, right? Because you have a single random process filtered by two different LTI filters. But whenever you have jointly distributed random processes, whether they are jointly Wise and stationary or not, you can define the joint power spectral density in this way. So cross power spectral density. So cross power spectral density, by definition, means what? The cross correlation between two components at the same frequency. Got it? It could be zero. It could be some non-zero number. If cross power spectral density at a specific frequency f0 is non-zero, what can you say? Two random processes have spectral correlation at the same frequency f. For example, f0. Now, in f1, the cross power spectral density is zero. What does that mean? F1 component in random process y1 and F1 component in random process y2, they are actually orthogonal, but if they are zero mean random processes, we may call uncorrelated. Got it? So that's the meaning of cross power spectral density. And let's go back to the special case. Then what do you have about the cross power spectral density in this case? So again, special. You can show that in the above setting, the cross power spectral density is nothing but the input power spectral density filtered by the frequency response of the first filter and filtered by the conjugate of the Fourier frequency response of the second filter. Now, what does this mean? And you may say that, well, it's a way to find the cross power spectral density in this special setting. You are right, but consider further specialized case, special. So here we assume that F1 and F2, sorry, not F1, H1 and H2 have what? They are, let's assume they are very, very narrow band ideal filters. But this is around centered at F1, and this is centered at F2, which is different from F1. Then, what does that mean? Your product, capital H1 of F times capital H2 of F conjugate is zero. So whatever value you have, zero if H1 of F, H2 of F is zero for all F, right? Of course, there are other conditions depending on this one, but we may sufficiently say that under this condition, this is zero, right? What is the implication of this very simple consequence of the result you learned in undergraduate or graduate probability random process course? This is zero, right? in this case. What does that mean? The above y1 and y2, above y1 and y2, has what? Has no spectral correlation if two different frequency f1, f2 are chosen. Got it? So here, this means that X itself, right? Assuming zero mean. Got it? Got it? So X of t is assumed Y-sense stationary. And Y-sense stationarity, implies actually orthogonality of the two components with different frequencies. But on the zero mean assumption, no spectral correlation. Got it? Now, my question is, can this result be generalized for this one? Right? We have vector valued Y-sense stationary random process. Got it? And we already know that Y-sense stationarity implies the existence of a single variable matrix valued function that is only a function of time difference, or delay, you mean, or lag. Got it? And if you Fourier transform each component, then you have some function of f. Now, what does this mean? So we do almost the same thing. Let's consider cross correlation or cross power spectral density here. Okay, some random ith component and jth component you take. Then this is the cross power spectral density, right? Now, what do you do? So you already have the idea. So you filter each element with H1 and Hi and Hj to obtain Yi and Yj. Anybody? What would be the cross power spectral density of these two outputs in terms of two inputs and two frequency responses? You already know, right? You can easily show this result. Now, again, what does this mean? You consider a very narrow filter, concentrated its passband around f1 and f2. Then this product is zero. Now, what do you have? You have the same result. And what's the implication? So let's remind of you the definition of the cross power spectral density. The correlation between two frequency components, one in Fyi, the other in Yj, at the same frequency f, right? And what does this say? It's 0. Now, this zeroness applies to any choice of ij pair with I not equal to j. Got it? Even if you choose I equal to j, actually we already know, right? As far as f1 and f2 are two different frequencies, Weiss and stationary random process has no spectral correlation. So actually, you may drop just this one for all pairs of ij. Got it? So let's go back to this one. Suppose you have a length capital N, vector Weiss and stationary random process. Then what can you say? The component random processes are jointly Weiss and stationary. It is assumed, right? Actually, the Weiss and stationarity of vector random process is defined as the joint Weiss and stationarity among pairs of random process, component random processes. So it's not a surprising thing. But what is surprising is that these random processes have what? No spectral correlation if two different frequency components are considered. Its self or cross correlation are just 0. Got it? So you now understand what is the implication of the assumption you may choose in your signal modeling in future research or some development. When you model your received vector valued random process as a Weiss and stationary random process. You not only assume in the time domain, your autocorrelation, matrix valued autocorrelation function is a function of only delay. In the frequency domain, what do you assume? No spectral correlation. Got it? That's why this course is entitled as the spectrally correlated random processes, blah, blah, blah. Got it? And joint Weiss and stationarity really gives us some 0 spectral correlation. Now, let's go back to the power spectral density or two-dimensional power spectral density of the original Weiss and cyclo stationary random process. So again, we consider a single Weiss and cyclo stationary random process. And here in your brain, you must have what? X has what? X has harmonic series representation. And this one-to-one mapper may be called harmonic series representer, but I myself named this as fresh vectorizer. Fresh. So you may not find this terminology in other literature. And here, what do you have? Got it? So you have a single scalar valued Weiss and cyclostationary random process And in the parallel universe, you have what? A vector-valued Y-sense stationary random process. And in the time domain, what does this mean? Again, you have Y-sense stationarity. Oh, by the way, mean. Constant. You can also show that if we assume, if we derive this one, you have a constant vector. So mean path, vector-valued mean path is a constant vector. And autocorrelation matrix has what? Has each ij's component only a function of tau. Be careful. This is a matrix. Got it? In the time domain, what was the corresponding property? Mu x of t equals mu x of t plus t for all t. And Rxx t1 t2 equals Rxx t1 plus t t2 plus t. Got it? In the frequency domain, what do you have? Your two-dimensional power spectral density, which is the entry by entry Fourier transform of this autocorrelation function, has what? Gross power spectral density of the component random processes. Now, here, the difficult part is what would be the power spectral density here. By the way, I believe none of you are familiar with this strange notation, right? We usually have defined the power spectral density of a single random process or vector-valued random process with single argument f. What is this? So to understand this one, you first define this power spectral density. And what would be the definition? What would be the definition? So if you remember the definition for the single random process, it could be defined this way. Am I right? Very simple. Simply, F1 component in X and F2 component in X after time truncation. Why do we have time truncation? Actually, not many students know why we time truncate, introduce the time truncate. And simply put, in order to compute this one, you have to consider every sample path, every realization of a random process. And most of the times in Y-sense stationarity or Y-sense cyclostationarity, each sample path is not a finite energy signal. And some of you are exposed about the difference between Fourier transform and Fourier planetary transform. And actually, Fourier transform, by definition, exists for every L1 function, which is absolutely integrable function. Unfortunately, what we electrical engineers want is that we want to solve some problem in the time domain, but we move to via Fourier transform in the frequency domain, and we want to go back to the time domain, right? The problem of L1 functions is that even though they have well-defined Fourier transform, some of the functions, L1 functions, may not have L1 function at its Fourier transform, which means that your inverse Fourier transform may not exist. So that gives us a headache. But Fourier planetary transform is actually most of the times just simply called Fourier transform. 99% of the electrical engineering professors teaching signal gen systems just call Fourier planetary transform as Fourier transform. That's why confusion occurs. But Fourier planetary transform is a transform for L2 functions, which means finite energy signals. And one good thing with finite energy signals is that if you integrate that signal by choosing a proper time origin and with some negative delta and positive delta to delta period, and then you increase the integration interval, then you have well-behaving integration, even if you multiply e to the negative j2 pi ft. So whenever you have a finite energy signal, Fourier planetary transform that time truncates your original signal and multiply e to the negative j2 pi ft and integrate converges. Exists. That is called the Fourier planetary transform of the L2 signal. Now, good thing is that every L2 signal has Fourier planetary transform that is also L2. So it's square integrable in the frequency domain. What does that mean? Again, by performing Fourier planetary transform, inverse Fourier transform, you can come back to the time domain. That's the power of Fourier planetary transform. The problem here is that, as I told you, actually this is Fourier planetary transform, and each sample path may not have finite energy signal. So we truncate as we do in the Fourier planetary transform. So we truncate and apply Fourier planetary transform. Then, under the assumption of second order, I defined that, right? Second order random process means finite power random process. And that implies the time truncated version has well-defined Fourier planetary transform. So you may call this as what? Approximately the F1 component in X. And this one is what? F2 component in X for sufficiently large delta. So as an engineer, this limit delta tends to infinity must be interpreted as what? For sufficiently large delta. Never forget this, right? Engineers wants to handle for sufficiently large or for sufficiently small blah, blah, blah cases. In that case, we use limit something tends to infinity or limit something tends to 0. Got it? When I was a graduate student, no one taught this fact to me. So whenever I handled limit something tends to infinity in communication systems or electrical systems, I just had no full understanding. But after I interpreted every limit operation as for sufficiently large or for sufficiently small something, I could get the so-called engineering sense of what does that mean. So never forget this. Okay? Anyway, so here you may say that, hey, this is nothing but the generalized version of the ordinary Fourier transform. Why? Because here you may claim this. Be careful. Again, this is another abuse of notation. Why? Because this S sub xx is what? A function from R into R plus, because power spectral density is always yeah, in this case, it's magnitude square, so it's R into R plus. And what about this function? This function is from R square into C. Got it? Assuming X is a complex valued random process. So some things similar occur again and again whenever we handle random processes. As we've seen in the definition of Y-sense stationarity, we had this abuse of notation. Even though they have the same name, right? There may be Junho Zhou in Pohang, right? And he may be an 8-year boy. He's different from me, right? Same. See that? These are x underscore, and this x underscore is a function from what? R squared into C, right? What about this function? This function is different even though they have the same name. This is a function from R into C. Got it? Anyway, so you have now the interesting relation between this power spectral density and where it is? And yeah, I didn't write. Anyway, that power spectral density, your conventional power spectral density. Okay, this is conventional one, and this is new one. Got it? Actually, this may have different values. Now, what would be the property here for Y-sense cyclostationary random process? Anybody? So let's utilize the result here. Got it? Let's utilize the result here and try to figure out or guess what would be the shape of this function. So here you have Xi1 axis and Xi2 axis. So I'm going to examine this function parameterized by Xi1 and Xi2. Got it? Now, if you restrict Xi1 to the Nyquist zone and Xi2 to the Nyquist zone, then what you want to do is to consider the value of this power spectral density at each point inside this square, right? Now, suppose you choose F1 and F2, then this point is the pair of F1 and F2. Now, this axis, actually axis for complex number, so it's two-dimensional. But anyway, let's think about what would be the value of here. What would be the meaning of this? Actually, xi1 equals f1 inside the Nyquist zone means that you consider what? In the vectorized, fresh vectorizer, you take the center element, right? You have a filter bank, modulator and low-pass filter. And in the middle, you have just no modulator, but the ideal low-pass filter, with passband, the Nyquist zone, right? Since you are thinking about F1 here, actually, here you need to consider X1, right, at F1. Now, what about this one? Again, X1 at F2. Let me say X0, because we have X minus L of T to XL of T in the vectorized Fourier transform, right? We assume 2L plus 1 components. So zeros 1, right? Zeros entry we take. Now, what is this one? What is X0? It's a Y-sense stationary random process with strict band limitation to the Nyquist zone, by definition. And what if this F1 comma F2 does not lie on this xi1 equals xi2 line? F1 is different from F2. Then its value, power spectral density, must be 0. Why? Because X0 of T is a Y-sense stationary random process. So only on this line, right? Only on this line, you may have non-zero value, right? Now, what would be that value? So you may want to say that, okay, it's just the power spectral density, right, at F1, because F1 equals F2. So if you consider this point, F1, F1, you may say that, okay, the height would be this one. By the way, what is this one? Oh, sorry, X1, X0, 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 right? The ordinary power spectral density of random process X0 at F1. Unfortunately, you are wrong, okay? Unfortunately, here, this line is not that one, but you have here, this one is just psi. Okay, so you have actually an impulse fence here. And this height of impulse fence is the ordinary power spectral density. And actually, this phenomenon occurs, not phenomenon, again, in your other graduate course, which started in the middle of the summer and only offered for my graduate student, right? At that time, I intentionally avoided the use of this delta function by considering a discrete time channel. In that case, you only have Kronecker delta function, not direct delta function. Anyway, so here, remember that this one is not just a 0 and some power spectral density. Actually, you have impulse fence, and its height is proportional to the power spectral density of x0. Now, similarly, you can generalize this argument for these seemingly diagonal tiles. Now, what about this one? Now, what about that one? That is, if you choose F1 here and F2 there, what? Actually, that is related, that part is related to what? At the output of the fresh vectorizer, this is what? The one branch above x0. So you may call this as x negative 1 of t's. Power spectral density will appear here. But be careful. This part is what? Right? Am I right? Oh, plus. Sorry. Yeah. So the negative 1's components power spectral density is shifted negative 1 over t. That's why we have plus 1 over t, right? By shifting. And again, you have impulse fence. And here, this part would be, if I remember correctly, yeah, something like this. And here you have dot, dot, dot. Got it? So all the power spectral densities appear here as what? As the coefficient to the impulse fence. Let me ask you a question. Are they the same or they may be different? They may be different, right? You may have different power spectral densities for jointly distributed, jointly wise and stationary random processes. So unlike the autocorrelation function, you remember in this autocorrelation function, what did you have? If this is T1, this is T2, what did you have? You have the same tile covering the diagonal parts, right? And same tile covers the first off diagonal. Same tile covers negative first diagonal, off diagonal, blah, blah, blah. However, in the power spectral density, the height of the impulse fences may be completely different in these tiles. Got it? Now, next, what would be the off diagonal tiles? So let's focus on this one, which is very simple. So here, what component random processes are considered here? Because Xi1 is limited to the zeroth Nyquist zone, and Xi2 is limited to the plus ones or positive ones Nyquist zone. We now consider the cross correlation between x0 of t and x1 of t, right? So this is actually, these two are what? Jointly wise and stationary random processes, strictly band limited. And we already know that their joint Y-sense stationarity implies spectral correlation only when they have the same frequency. But the difference is that here, in the, where it is? Yeah. In the harmonic series, remember that, when each component random process contributes to the original Y-sense cyclostation random process, you have kind of carrier multiplied. That's why I shifted this way. This plus 1 over t, plus 2 over t, minus 1 over capital T are all due to this one. Got it? Now, due to the shift, actually, this one is what? This one is the frequency component f1 equals 0 for, f1 equals 0 for x0. And even though this is here 1 over t, actually f2 equals 0 for x1 over t due to that shift. Got it? So again, you have here as x0, x positive 1 of, now let me see, f1, psi 1. And now here you need to shift up by 1 over t. So what is the case argument equals 0? This is 0 means that xi2 equals x xi1 plus 1 over t. So this line, as you learned in high school math, right? Got it? So you can continue this forever, right? For every type. And what will happen? You need a leap of faith. And suddenly, your power spectral density with xi1 and xi2. By the way, that has, some people say bispectrum. Okay? It has many, many different names. It was reinvented by many, many persons, many, many researchers in many different area of academia. And probably bispectrum would be, bi-power spectrum would be the easiest name. Got it? We will be back in one of the papers, because when I just said that the generalized power spectral density or something, one of the reviewer pointed out that it has many names. And from that on, I used bispectrum or some other similar names. Anyway, so interesting thing is that anyway, you have xi2 equals xi1 line. You have xi2 equals xi1 plus 1 over t line. And all the parallel lines. And you have xi2 equals xi1 minus 1 over t. And all the lines. And on these lines, on these parallel equally spaced lines, you may have non-zero power spectrum value for x of t, which is assumed Y-sense cyclostationary. And on these lines, you have actually impulses. So you have impulse fancies. And its value could be complex because we assume x of t is general complex valued y-sense cyclostation random process. So actually it's hard to visualize, but you know what I mean. Got it? By the way, spacing is not measured this way. Okay, spacing is measured parallel to the horizontal and vertical lines. Got it? So by inspecting that bispectrum, you may easily see the cyclostationarity. Now, let's reinterpret this figure just without using the harmonic series representation. Now, let's choose some F1 here and some F2 there. Got it? Then you have what? You have a point F1 comma F2. In this choice, my arbitrary choice, F1 and F2 has what? Has no relation like this. So the difference between F1 and F2 is not an integer multiple of the cycle frequency. By the way, the cycle period is capital T, and its inverse is called cycle period of the random process. Anyway, so here, if F1 minus F2 is not an integer multiple of the cycle frequency of, or if you want the inverse of the cycle period, then what? Your spectral correlation is 0, under the assumption that you have 0 mean random process. Got it? What about the other case? So the difference between, 2, 0. Then you have spectral correlation. And be careful when you interpret this one. Even though you have impulse, that does not mean F1 component in X and F2 component in X has infinite correlation. It's height. It's very confusing in talking about height of impulse, but the height of the impulse is the correlation. Got it? So probably after you learned harmonic series representation, and especially your mind that transforms a y-sense cyclostationary random process to a vector y-sense stationary random process, you would be never want to talk about this bispectrum that has infinite impulse fans. Why? Here, you don't have impulse fans. See that? This one is a single variable power spectral density, even though its ijth component is related to the cross correlation between two random processes. Why? Because we consider cross correlation of two random processes at the same frequency. Got it? So no impulse here. Be careful. So now, even though my paper, the 2004 paper, talks about impulse fancies, and even some later papers also talks about that, forget about it. Just whenever you see a y-sense cyclostationarity, you have in your brain, okay, I don't have a scalar valued y-sense cyclostationary random process. That has some strange impulse fence in two-dimensional bispectrum. I will think it as what? A vector valued y-sense stationary random process. Y-sense stationary vector valued random process. The problem is that you are not actually asked to process a vector valued random process. That's why last time, probably many of you wondered why I said that, but Suppose you have an LTI filtering. This is what? This is equivalent to this one. So, by the way, here X needs not to be a Y-sense cyclostationary random process. You may choose arbitrary here. You may choose arbitrary fresh vectorizer. Because this equivalence holds for any choice of capital T. Got it? However, what value of capital T do you want to choose if this is a Y-sense cyclostationary random process with cycle period capital T? You want to choose fresh vectorizer with parameter capital T. Why? This becomes a vector Y-sense stationary random process. If you choose different capital T from the cycle period, even though you have equivalence, you can't enjoy Y-sense stationarity of the input and Y-sense stationary of the output and joint Y-sense stationarity of the two input-output vector valued random process. Got it? So be careful. But anyway, so this is the way. So by doing this, you can save a lot of time to understand the papers in the reading list, even though many of the early papers do not seriously talk about this conversion. Got it? Whenever you think in this way, everything becomes simple. Got it? Okay. So we are almost done with the harmonic series representation. And I've decided not to cover the time series representation because that will appear when we study other paper in the list. Got it? For the time being, I believe this harmonic series representation is a headache to you already. Got it? Then, in order to finish today's class, I will give you an interesting thing here. Now, suppose, by the way, this double line, two-lined arrow means vector valued signal in, vector valued signal out. What if you have not that general, but this is of course, this is an abuse of notation because x underscore of t is not a complex number. Actually, this means x underscore has range, this one, right? So this is an abuse of notation, my own notation, never write in your paper, okay? Just for simplicity. And now let's assume that this capital H of t, the impulse response, matrix valued impulse response of an LTI system is square matrix. Then you have, of course, the output range C to the N. Now, what should be written here? What is the property of this one? By the way, many of you are already exposed to multiple input, multiple output system when you study digital communications in undergraduate level or in a graduate level, right? Because these days, multi-antenna system mathematically modeled as multi-antenna channel transmit, multiple transmit antennas, multiple receive antennas, then this radio channel can be modeled as what? As a MIMO system, right? Multiple input, multiple output system. So you are familiar with what I mean. So here, output is the convolution between h of t matrix valued function and x of t vector valued signal. And what is the nth entry? Anybody? It's very similar. So m runs from 1 to capital N. You have h of t and m comma n convert with x n of t. Got it? This is just an extension of what? Suppose you have a vector x that is the product of square matrix H and X. Then what is the mth entry of Y? It's m n x n summed over n, right? So what is this one? This is mnth component of this matrix valued function. So this is actually scalar valued function. You may say this as h, m, and t convert with x, x, n, n. Got it? So you are familiar with a MIMO system, continuous time MIMO system. Of course, many of you already have taken, not many of you, I believe everyone has taken linear algebra, introductory linear algebra or advanced linear algebra in your undergraduate and graduate courses. This is simple extension, right? Now, again, today's last question. What kind of system is this that makes equivalence between an LTI filtering of a vector valued signal in the time domain? Got it? What would be the property? So first, naive question or naive attempt would be, is it an LTI system? Then your answer is no. Why? I already told you. If this is an LTI, then that matrix must be a diagonal matrix. But here, I didn't say it's a diagonal matrix. It's just a square matrix with possibly non-zero diagonal component function. Then what? Is there any non-linearity here? No. But there is time variance. Why? Because the relation between x and x underscore is what? It's that of the harmonic series representation. So each element is actually modulated with different carriers, or each element modulates different carriers, and then its sum is x. Whenever you have modulator, the system is no longer a linear time invariant system. It's still linear, however, not time invariant, which means it's linear time varying system. So in general, this box must have what? 2-parameter impulse response, ht tau. And your output must satisfy this relation. So we now know that the system must be a linear time varying system. But that is not the complete answer yet. There are many linear time varying systems. But this is very special. And anybody? What would be the property of this kernel, or actually impulse response, time varying impulse response of this linear system? And you will surprisingly will find that you have this property. Is it very similar to the property of the autocorrelation function of the Y-sense cyclostationary random process? Yes. Right? You remember in the definition of the Y-sense cyclostationarity of a single scalar valued random process, what was the mean path and what was the autocorrelation function? Mean path must be periodic with period capital T, and your autocorrelation function as a function of T1 and T2. They must be what? Equal to, it must be equal to the autocorrelation evaluated at T1 plus capital T, comma, T2 plus capital T. Same thing happens here. The impulse response, time varying impulse response of this system is what? Periodic in some sense. Periodic in T actually, and periodic in tau. Or it's invariant under origin translation by integer multiple of T. Got it? Got it? By the way, if you are not familiar with two-parameter impulse response for general linear time varying system study, you can find a lot of materials from the internet, and you yourself can derive this result without much difficulty. As far as you remember how you derive the convolution integral gives you the output of the linear time invariant system. You follow almost the same procedure as you derive the output y is the convolution integral between the input signal and the impulse response for a general LTI system. You can do almost the same thing for a linear time varying system. The key is to rewrite the signal input x using the shifting property. So if I write very quickly, because many of you just close and open your eyes. Got it? So your LTI system's response to the time signal, time parameterized signal. So this is what? In the t-axis at tau, you have impulse. So general LTV system has different responses for different impulses located, delayed relative to the origin. That function is called h of t, parameterized by delay of the impulse. This is the impulse response, and we just use the commutativity of the multiplication of any two complex numbers. Got it? So this is the generalization of the convolution integral for linear time varying system. That's why I have claimed that this is the this is the input-output relation. I didn't prove yet why this ht tau must satisfy this property yet. But anyway, it's enough. It's good to expose the result to you before any proof, because you can now kind of have a lot of similar things working around this course, right? You have elephants and mammoths and looking very similar, big and just small. Got it? Okay, that's all for the day.